Hi, everyone. All right, let's look at example 9-6. So this is one of the example problems in your textbook. Okay, so let's solve this problem together. All right, so this is example. Let me use the, example 9-6. So the problem is this: determine the LRFD design moment capacity and the ASD allowable moment capacity of W24/62 with Fy of 50 KSI with a given unbraced length LB is equal to 8 feet, and since the B value is 1.0. So you might remember this chart. So here we have, sorry about, let me do it again. Okay, so this is better. Here, the x-axis is the unbraced length or unsupported length, and the y-axis is nominal moment. And our chart for the moment capacity looks something like this. So this is the value L sub P, here L sub R. So L sub B is a variable. If this unsupported length is either 0 or less than L sub P, then we can maximize our capacity. Let me use a different color. Okay, so the corresponding capacity in this region, Mn, will be equal to Mp, which is Fy times Z, right? If L sub B is between L sub P and L sub R, and we have an equation, M sub N, different equation, which looks like this: C sub B times Mp minus Mp minus Mr times, you have two different length difference, LB minus LP, and in the denominator it is LR minus LP. And of course this Mn should be less than or equal to Mp, which is this value here. And if L sub B is larger than L sub R, we are in this region. You remember that this chart, right? And we have very complicated equation for Mn. So I said we don't need to worry about this in this class. Okay, all right. So let's look at the problem again. We have given section which is W24/62, and given L sub B, the unsupported length is 8 feet, and then Fy is 50 in KSI. So first thing we have to check is, and let's just focus on one of the method, let's say LRFD. So let's solve the problem using LRFD method. The first thing we have to do is that we need to go to table 3-2, which is a table for the beams, pre-calculated the capacity, and it is in your steel manual, of course, for this specific section. So 24/62. So 24/62. Here we go. Is 24/62. Yeah, 24/62 is here. So I'm gonna just change it to screen. All right, so here we have my steel manual. Okay, so we are going to start from here. 24/62 section is here, and this is the pre-calculated phi times Mp, which is the factored nominal capacity, the plastic nominal capacity, which is going to be the maximum value. Since we are using LRFD, the value is 564 or 74, right? And this is the phi times mr, which is the component of our mn equation, 344, and bf, we already talked about that in the previous slide. For LRFT is going to be 24.1. But the first thing you have to check is whether our unsupported length is less than L sub p or larger than L sub p and less than L sub r. So we have to look at the range of our, the location, the position of our L sub b. L sub b was 8 feet. For this given section, 24 by 62, L sub p is 4.87 and L sub r value is 14.4. So that means our value of L sub b, the unsupported length, was 8 feet, which is in between L sub p and L sub r, right? So let me go back to my calculated one here. So this is our given value, and L sub p, I said, is 4.84. So for this given section, L sub p is 4.87, and L sub r is 14.4 in feet. So as you can see, this 8 feet is in between these two, which means we have to use this equation. This equation is to find out our nominal capacity for this given section, 24 by 62. So I'm going to copy the number first for W24 by 62. Using LRFD, we need V times MP, which is 574, V times MR, which is 344, and V times BF is 24.1. And I already copied the LP and LR here. Okay, so let's just close my manual. All right, so how can we calculate our nominal moment? Nominal moment for this section using LRFD eventually is going to be phi times mn, which is, and the given value for C sub b was 1.1, right? So let me just say this is 1, then phi times mn is going to be phi times mp. So I'm going to multiply by phi for everything here, right? And then phi here. And I said that mp minus mr divided by lr minus lp, this is equal to bf, right? So this minus v times bf times lb minus lp will be our nominal vectored moment. Okay, so just plug in those numbers. V times mp, 574, minus V times BF is 24.1. We actually don't need this V times MR because that's already included in our BF calculation. So this times LD, which is 8 feet, minus LP, 4.87. So when I calculate this number, I got 499 kip feet, which is less than 574. So that is good because we have to make sure that this vectored mn using this equation should be less than phi times mp, which is the maximum capacity of our beam, the maximum plastic capacity. So therefore, our vectored nominal moment is going to be 499 kip fid as our final answer. Okay, pretty easy and straightforward if you understand how to use this steel manual. All right, let me go over to, I think this is going to be the last example problem. I initially thought example 9.9-9 would be interesting, but I don't think that is going to be used in this class. So let me go on to the next example, problem 9-8. Okay, let me just clear the drawings. Okay, so here's a problem. Using 50 KSI material property, still, select the lightest available section for the beam of figure 9.14. I'm going to draw the loading conditions and the boundary condition in a minute, which has a lateral bracing provided for its compression flange only at its ends. And we're going to assume that CB is equal to 1.0 for this example, and it's actually 1.14. I'm going to talk about that in a minute, and use, let's see, ASD method. Okay, so this is example 9-8. And here's a beam. This is a simply supported beam. And then we have a uniformly distributed load on top of this beam. The loadings are, so the dead load is 1 kip per feet. And this doesn't include the beam weight. Okay, and the live load intensity L is going to be 2 kips per unit length. Okay, so those are the loading conditions, uniform distributed load on top of this beam. And the entire span of this beam is 20 feet. And there's one specific information about the lateral bracing. It says that it has a lateral bracing provided for its compression flange, which will prevent the lateral torsional buckling, right? Only at its ends. So we do have a lateral supports, but not along the entire length of the beam. We only have the lateral bracing at each support. So what it means is that we do not have any lateral support in between, but we do somehow like going through additional member connected to that that beam at the support, or we could have a literally bracing there, or we have a connected slab or something like that to prevent lateral torsional buckling in our compression flange, only at the support. So this information automatically says that our L sub B, the unsupported length, will be equal to our L, which is 20 feet. Okay, if we have this entire beam is going to be braced in the lateral direction through the slab, for example, that's one of the previous example problem, right? Then L sub B is going to be 0. Depending on how many or how often we have a lateral bracing, that will determine the unsupported length. In this case, since we only have the lateral bracing at the supports only, then L sub B is going to be equal to 20 feet. Okay, and I also said the C sub B is going to be assumed as 1.0. This is based on the assumption. And by the way, we already talked about the C sub B factor, which is provided by the table 3-1. So I'm going to go back to table 3-1 from our steel manual. So here is table 3-1. You may remember this table. So values of C sub B for simply supported beam. And we have the very bottom. Okay, I'll show you. So this is the very bottom of the table. So this table provides several different typical loading conditions when we have the concentrated force in the middle, here 2 concentrated forces, 3 concentrated force, and this is another typical case that we do have the uniform distributed load. And this one, the second column shows us where do we have letter bracing along the span. So if there's nothing, no bracing within the span, but we only have the letter supports, a letter of bracing at the supports, then the corresponding C sub B value is going to be 1.14. So in our case, the actual and accurate C sub B value should be 1.14, but the problem says we're going to just assume C sub B is equal to 1.0 to make our problem simple. Okay, so I'm going to use a C sub B value of 1.0 then, based on the given assumption. So that's what I'm going to use for C sub B. And then another given condition was Fy. Fy was equal to 50 KSI. All right, so let's calculate, let's select the section. So selection of W shape based on the given boundary conditions and the given loading, which is a design problem, right? So design problem, we always start from the load calculation because based on the loading combination that will provide our target demand. In this case, we do know the dead load, but it doesn't include the beam's weight because we do not know how much weight is gonna be for our final selection. So what we're gonna do, like the other previous example problem, we're gonna calculate the target demand based on the given dead load and live load without having the beam's weight first. Select the section, and based on that selection, we're gonna include the beam's weight of that trial and then pick another section based on that. So we're gonna do that. Change the color. Okay. So did I say AST? Yeah, because the previous example I used LRFT. So I'm gonna use AST method for this problem, but your textbook has solution for both AST and LRFT. So AST, we have WA. So WA is gonna be the intensity of our, the uniformly distributed load. Since ASD, the load combination is simply D plus L, right? There's no factor. For LRFD, of course, we have 1.2 and 1.6, those factors. And instead of WA, we calculate WU, that is the factored intensity. But in this case, it is going to be WA, which is D plus L. So 1 plus 2 is going to be 3. So 3 kips per feet is going to be our intensity. And under the uniform distributed load, in my previous video, I explained about how we can calculate the maximum moment under the uniform distributed load. That is going to be WL squared over 8. So W is going to be 3. WL squared is 20 squared over 8. Then it is going to be in feet unit. So when I calculated, I got 150 feet of the moment. So this is going to be our target demand. Okay, so our selection should be based on this number, 150 feet. But again, this one doesn't include the beam's weight, right? So we will have the first trial based on this number. But after that, we're going to include the beam's weight. Okay, so the design problem, we are going to use table 3-10. So I'm going to use a table 3-10. I'm going to show you how to use this. Okay, so table 3-10 in your steel manual, it looks something like this. So this is exactly the chart that I explained about MP between L sub P and L sub R, depending on the unbraced length, we have a different, reduction of the MN. And this is the chart for all the sections overlapped together. So our target demand was 150 as a first trial. So, and we are using ASD, right? So this is how this chart, we can read this chart. So it looks something like this. Here we go. It looks something like this. So in the x-axis, this is based on the unbraced length or unsupported length, L sub B. And this y-axis is based on the factored nominal moment. So using LRFT says d times mn, ASD is going to be mn divided by omega. Since we're using ASD, we're going to go follow this line, and our target demand was 150. So I'm going to go on to the next page until we can see that range of the number. So this is up to 160. So this is the one. But this chart has unsupported length up to 18 feet. So we have to go on to the next page, which will provide from 18 feet to up to 34 feet. Okay, so let's use this chart. And I said our corresponding 100, the vectored moment was 150 using ASD. And ASD, the one tick is a 1 kip increment. So here we have 148, right? 149, 150, 151, and 152. So 148, 9, and 10. So this is going to be 150, right? So, all right. So here is 148, 9, and 10. So this is the tick 450, and we have to look at the intersection with our unsupported length of 20 feet. So 20 feet is here. So we're going to go up with the 20 feet up to 150. So this is going to be the intersection point. Can you see it clearly? I'm doing my best, I think. Yeah. So this bolded line is 20 feet unsupported length, and this is the tick for the 150 kip feet. So this is the intersection point. How can we read this table? Well, we're gonna find out the first solid line into the right and above the range. So we're gonna go this way, right? And to find out the first solid line, which is this, right? And the corresponding section is right here, which is 12 by 53. So 12 by 53 is gonna be our first trial. So I'm gonna write down that section here. So I said, so from table 3-10 with 20 feet of L sub B and 150 kip feet using ASD, we find out the intersection point, right? Like this. So this is 20 feet. Here we have 150 kip feet. And then we're gonna read the chart this way. So find out the first crossing the solid line. The solid line is going to be the lightest section within that group. Dotted lines are the heavier section, that the solid one. So find out the first solid line that was W 12 by 53. So this is going to be our first trial. And as you can see, the weight of this section is what? 53 pounds. So 53 pounds per feet, right? So now we're gonna update our moment calculation, including this beam's weight. So earlier I said 3 times 20 square over 8. Now our MA is gonna be modified and updated as what? 3 plus 0.053, so that we have initial dead load and live load here, and then including the dead weight of the beam, and then 20 squared over 8. When you calculate the maximum moment, it is going to be 153 kip feet. Okay, so now we're going to go back to the chart and then do the same thing. instead of 150 now, this is going to be 153. So our point is going to be somewhere here. And when you read the chart again, it will give us the same answer actually, 12 by 53. So therefore, we're going to use W12 by 53 section based on this given span length with this given loading. So this section is going to be good enough to support the load. And if you'd like to find out the factored moment, which is 153.6 kip feet, which is larger than our MA. So this is okay. All right, so this is how we can solve the problem using table 3-10. This is the design problem, all right? So depending on the unsupported length and the given loading, we pick the section, and using the chart, we find out the lightest section within the range, and we double check whether that the maximum capacity is still larger than demand. All right, so this is the end of video for this week, week 12. Okay, so have a nice weekend, and then I'm going to post another video clip for week 13. Week 13, we will have a review session and then the second midterm, and that's it. All right, and I already assigned the entertainment package for you, so you're gonna work on and enjoy that entertainment package over the week. So this Friday is gonna be the Good Friday, and this next coming Monday is gonna be the Easter Monday. So I do not expect you to have any learning on those days because those are the university holidays. But so the following week, I'm gonna post the review session for the midterm number 2, and then on Wednesday during our class time, I'm gonna make the test available on the Blackboard. So in the review session video, I'm going to talk more about how you're going to take the midterm exam and how you're going to provide your work through the Blackboard in that video. All right, thank you and have a great weekend. Bye.